lecture series on complex analysis for undergraduate students. Today's lecture is evaluation of real integrals. We are learning till now the integration methods for complex integrals, contour integrals, complex functions. We had learned one important result, residue theorem and residue integration method, which was very helpful in evaluation of many contour integrals. Today we would see that residue theorem does not only help in evaluation of complex integrals, but it also helps to find out the integral or evaluation of integrals of the real functions and the real integrals. In this series, let us first see the definite integrals. First we would see the definite integrals of those functions which are involving sine and cosine function. So, let us consider the integral of type 0 to 2 pi, a function of cos theta sin theta integrated with respect to theta. This f cos theta sin theta, this is a real function. Moreover, we are assuming that f is a rational function and it takes on finite values in whole interval of integration. That is, it never goes infinite at any point inside the interval of integration. Now, we would first actually change this real integral into a contour integral or integral of the complex function, and then we would use this residue theorem to solve this integral. So, let us say we are making this transformation z as e to the power I theta. We do know that cosine theta is 1 by 2 e to the power I theta plus e to the power minus I theta, or we could write it as 1 by 2 z plus 1 by z. Similarly, we do know that sine theta is 1 upon 2 I e to the power I theta minus e to the power minus I theta, that is, we could write as 1 upon 2 I z minus 1 by z. Now, what is this z is equal to e to the power I theta? For the range you are having is, that is, for theta is ranging from 0 to 2 pi. So, here if I take theta is ranging from 0 to 2 pi, z is equal to e I theta, this is nothing but the parametric equation of unit circle. So, we are having is, that is, now this function, if I substitute cosine theta and sine theta as the functions of z and 1 of z, we would get actually a function of z only. So, f cosine theta sin theta would be, say, small f of z, some function of z. Of course, it will involve z and 1 by z. Moreover, dz would be actually d theta you could write as dz from here e to the power I theta d theta. So, d theta would be dz upon I z. What it says is that we could write this integral 0 to 2 pi, a function that is capital F of cosine theta sin theta d theta, as a contour integration on the unit circle C of a function small f z dz upon I z, that is, d theta is dz upon I z. So, rather I am writing it as integral of f z upon I z dz on the contour C. And where, what is this contour C? This contour C is nothing but the unit circle mod z is equal to 1. So, you see, if I am having this definite integral which is involving sin theta and cosine theta and ranging from 0 to 2 pi, something like that, we could get is that we can change it to the contour integral on the unit circle. Let us see one example to understand this method. Evaluate the integral 0 to 2 pi d theta upon square root 2 minus cos theta. If you do remember your school mathematics, this integral is not really very nice integral on which we would be happy to see that we can do this integral. Let us see using this residue method how we could find it out, and rather actually we will do today examples in which so many integrals you had used as the formulae. So, let us first find it out that using this the method which just now we had learned, what we would do is we would transform this theta to z. using this transformation z is equal to e to the power I theta. So, d theta would be dz upon Iz, and here it is involving only cosine theta. So, cosine theta we do know, we could write as half of z plus 1 by z, and then this integral would be changed to the unit circle. So, integral 0 to 2 pi d theta upon square root 2 minus cosine theta I could write as contour integral on the closed contour C. 1 upon root 2 is as such, cosine theta we are substituting as z plus 1 by z by 2, and d theta we are substituting dz upon Iz, and this contour C is your unit circle. Now, simplify this function so that we do have what this function is actually. If we do simplify it, you do get it as upon 2 here is and this I is here. So, I would take this I up and I would write it as minus I. So, I would get 2 I, and from here we would get actually square root 2 z minus z square minus 1. So, minus sign I am taking out, I would get z square minus root 2 z plus 1. So, what we have got, this integral is simplified form 2 I upon z square minus 2 root 2 z plus 1 dz on the contour unit circle. Now, this function is of the form is some constant upon a function. So, certainly it would be it would cease to be analytic at certain points. What would be those points? Of course, the points where this denominator is 0. So, we have to find out where this denominator is 0. Let us see is that is we could write it out as, because it is z square minus 2 root 2 z plus 1, we could just get its fractions as z minus root 2 minus 1 into z minus root 2 plus 1. Now, you see is this says is that zeros of this denominator would be at your root 2 plus 1 and at root 2 minus 1. That says is this integrand is a function which is having isolated singularities at root 2 plus 1 and root 2 minus 1. My contour of integration is unit circle. So, certainly my root 2 minus 1 would be inside this one, but root 2 plus 1 would be outside. So, f z has simple poles at root 2 minus 1 and root 2 plus 1. So, root 2 minus 1 is certainly the point which is inside the contour. So, now we are having is that the given integral can be transformed to a contour integral of a function, and the function is such that it has isolated singularity at a single point inside the given contour, and the contour is our unit circle. So, now I can use the residue integration method that says is I have to find out the residue of this function at this isolated singularity root 2 minus 1, because this is outside our contour region. So, let us find out the residue of the function 2 I upon z square minus 2 root 2 z plus 1, that we are writing it as the fraction form, that is 2 I upon z minus root 2 minus 1 into z minus root 2 plus 1. I have to evaluate its residue, I have to calculate actually its residue at the isolated singularity root 2 minus 1. So, I would use our first formula for simple pole for evaluation of residue, which says is that residue at z is equal to z naught, where z naught is a simple pole, is limit as z approaches to z naught, z minus z naught into f z. So, by that formula we would get residue at root 2 minus 1 of f z as limit z is approaching to root 2 minus 1 of z minus root 2 plus 1 into f z. That would be actually from here this portion would get cancel it out, and what we would get 2 I upon z minus root 2 minus 1, limit as z is approaching root 2 minus 1. So, this limit if we have to calculate, we have to simply evaluate at z is equal to root 2 minus 1. So, if I write z is equal to root 2 minus 1 here, I would be getting is root 2 and minus root 2, they would get cancel it out, and minus 1 and minus 1, that is minus 2. So, I would be getting it as minus I. So, now using this residue method, we would get the integral of 2I upon z square minus 2 root 2 z plus 1 on the unit circle, the contour is unit circle, is 2 pi I into the residue at the singularity, that is that is at root 2 minus 1 is minus I, we are getting is 2 pi. So, we have got this integral of the function 0 to 2 pi 1 upon the square root 2 minus cos theta d theta as 2 pi. So, you find it out, that is such a simple way we could find out this integral using residue method. Now, let us consider the integrals of this type 0 to 2 pi f a function of cos a theta and sin b theta. First one I have taken is that the function of cos theta and sin theta. Now, we are having is cos a theta and sin b theta. Can we change this kind of integrals also in contour integrals, so that we could use the residue theorem? Let us see, again what we are assuming is that my f is a rational function and it does not becomes infinite in the interval of integration. Use the same transformation, z is equal to e to the power I theta. Then we do know that d theta as such this one. So, we do know that cos a theta we could write as 1 by 2 e to the power I a theta plus e to the power minus I a theta. Now, we will play a little bit role because this is exponential function, and with many good properties of exponential function, we could write it as e to the power I theta to the power a plus e to the power minus I theta to the power a. E to the power I theta from here is z. So, it would be actually z to the power a, and e to the power minus I theta would be actually 1 upon z. So, it would be actually 1 upon z to the power a. So, what we have got cos a theta we could write as 1 upon 2 z to the power a plus 1 upon z to the power a. Similarly, this sin b theta we could write as 1 upon 2 I e to the power I b theta minus e to the power minus I b theta, which I could write as this 1 upon 2 I as such. E to the power I b theta we could write e to the power I theta to the power b and minus e to the power minus I theta to the power b. So, what we would be getting is z to the power b minus 1 upon z to the power b into 1 upon 2 I. That says is that again we can transform this kind of integrals with taking this transformation z is equal to e to the power I theta, and theta is ranging from 0 to 2 pi, says is that on the contour integration on the unit circle. So, integral on the unit circle of now this function is suppose this function is a function of z a small f z upon I z d z. Let us see an example again for this kind of things. Evaluate the integral 0 to 2 pi cos 3 theta upon 5 minus 4 cos theta d theta. I think you might be remembering that this integral you had solved somewhere in your school. Solution: we would transform this integral into contour integration. For that, we will transform this theta to as using the transformation z is equal to e to the power I theta. Then d theta is nothing but dz upon I z. Now, cos 3 theta is 1 upon 2 z. Cos 3 theta we have the formula that cos a theta is z to the power a plus 1 upon z to the power a into 1 by 2. So, here your a is 3. So, it would be half z cube plus 1 upon z cube, and cos theta is of course half z plus 1 by z. So, now substitute all these values in this integral. So, the integral 0 to pi cos 3 theta upon 5 minus 4 cos theta d theta can be written as the contour integral along the unit circle C as half z cube plus 1 upon z cube upon 5 minus 4 times. So, 4 is here 1 by 2. So, minus 2 times z plus 1 by z into dz upon iz. D theta we are replacing by dz upon iz. This would be on our unit circle. Now, let us simplify this function. See the numerator. Numerator here is we would get is z to the power 6 plus 1 upon 2z cube, and in the denominator we would get from here 5z minus 2z square minus 2 upon z, and this 1 upon iz is also there. So, this z would get it cancelled out with this z, and this z cube I would get in the denominator. Moreover, this 2 also will get commas in the denominator. So, what we would get actually in the numerator, z to the power 6 plus 1, 2z cube that is coming in the denominator, I is also going in the denominator, 5z minus 2z square minus 2. Now, this I will take into the numerator, that says is 1 upon I is actually minus I, and this minus sign I would take inside this one. So, I would get this denominator as 2z square minus 5z plus 2. So, I could rewrite this integral as I upon 2 contour integration on the unit circle C, z to the power 6 plus 1 upon z cube. Now, 2z square minus 5z plus 2, we can factorize it, we could get 2z minus 1 into z minus 2. So, this given real integral we have changed to the contour integral, and the contour integral of a function which is of the form pz upon qz. So, certainly this function will have some because this numerator is this denominator is having some zeros. So, this will have isolated singularities. Let us see what are the zeros. The denominator does has 0 at z is equal to 0, z is equal to half, and z is equal to 2. Now, let us see what kind of this denominators these zeros, and so accordingly what kind of isolated singularities we are having for this function, and how many of those isolated singularities are lying inside our contour region. So, I upon 2 z to the power 6 upon z cube 2 z minus 1 z minus 2 d z, this we have to evaluate on the unit circle. Now, this has a simple pole at z is equal to 2 and at z is equal to 1 by 2, but you see the denominator has this another 0 which is of the order 3. So, this f z will have a third order pole at z is equal to 0. So, now what we are having is we are having 3 isolated singularities 0, half and 2. Out of these 3 isolated singularities, if we see in our region of this contour is unit circle. Unit circle means this 0 would be inside this unit circle, half would be of course certainly inside this circle, but this 2 would be outside this unit circle. So, we have got that this contour is having 2 isolated singularities inside the contour. So, I am evaluating a contour integration on the closed contour where the function f z is analytic except at some finite number of isolated singularities. That says is we can use the and those isolated singularities are actually in this particular case are the poles, while as actually at z is equal to half we do have simple pole, but at z is equal to 0 we are having a third order pole. So, we can use the residue theorem, and for that we require the poles at 0 and at half. So, let us see that using the residue theorem we could say that this integral I by 2 contour integration on C of z to the power 6 plus 1 upon z cube into 2 z minus 1 into z minus 2 d z should be I by 2 times this integral is using the residue theorem 2 pi I times residue at z is equal to 0 and at z is equal to half. So, we have to calculate the 2 residues at z is equal to 0 and z is equal to half. Let us first see this z is equal to half, because this is a simple pole. because it is a simple pole and my function is z to the power 6 plus 1 upon z cube into 2 z minus 1 into z minus 2. I would simply, because in this fraction form, I would simply use the first method of calculation of simple residue at simple pole as limit z is approaching to half z minus half into f z. If I am multiplying with z minus half we could write as 2 z minus 1 upon 2. What I would get is z to the power 6 plus 1 upon 2 z cube into z plus 2. So, limit as z is approaching to half of z plus 6 plus 1 z to the power 6 plus 1 upon 2 z cube into z minus 2. So, as z is approaching to half, this limit would be just evaluating it at z is equal to half. Z is equal to half says this z to the power 6 would be 1 upon 2 to the power 6 plus 1, and here what we would get is 2 in times 1 upon 2 to the power 3, and here is half minus 2, that says is minus 3 by 2. So, minus 3 by 2 and this 2 I would get it, cancel it out, I would get here minus sign and 1 by 2 cube, here we are getting is 1 by 2 6. So, we write it 1 plus 2 to the power 6 upon 2 to the power 6 into 1 by, so we would get 2 to the power 3 here into minus 3. So, finally, what we would get it as actually 2 to the power 6 plus 1, 2 to the power 6 is nothing but 64, it is very easy, we always do this kind of calculations. So, 2 to the power 6 is 64 plus 1 is 65 upon your 2 to the power 3, that is your 8 into minus 3, that is minus 24. So, what we are getting is minus 65 upon 24. So, residue at the simple pole we had calculated that z is equal to half is minus 65 by 24. Now, what is remaining is residue at z is equal to 0. 0 is not a simple pole, it is a third order pole. So, we have to find out the method of calculation of residue of the third order pole. We would use the formula, that is for a residue to calculate a residue at a mth order pole at z naught, it is 1 upon factorial m minus 1, the m minus 1th derivative of z minus z naught to the power m into f z evaluated at z is equal to z naught. So, here my m is your 3. So, and z naught is 0. So, what we would get from here, the residue at z is equal to 0 for our given function f z would be 1 upon factorial 2, the second derivative of z minus z naught, that is z cube into f z evaluated at z is equal to 0. F z is z to the power 6 plus 1 upon z cube into 2 z minus 1 into z minus 2. So, z cube would get cancel it out, we would get here 1 upon 2 second derivative of z to the power 6 plus 1 upon 2 z minus 1 into z minus 2 evaluated at z is equal to 0. Now, let us say we have to find out the second derivative of this function. We will go one by one. Let us first find out the first derivative and then the second derivative. So, the derivative of z to the power 6 plus 1 upon 2 z square minus 5 z plus 2. We will simply use the method for the multiplication of two functions. It would be 6 z to the power 5 upon 2 z square minus 5 z plus 2 as such, minus the integral of this function as such and derivative this because this is 1 upon. So, that is why it is minus upon 2 z square minus 5 z plus 2 whole square, and the derivative of this is, you see, 4 z minus 5, that will come in the numerator. So, we have got 6 z to the power 5 upon 2 z square minus 5 z plus 2 minus z to the power 6 plus 1 into 4 z minus 5 upon 2 z square minus 5 z plus 2 whole square. This is the first derivative. The second derivative would be the derivative of this first derivative. So, now let us calculate the derivative of this. This is again the derivative of two fractions. So, again we will go with the multiplication of functions rather than the formula for the fraction. Calculate this derivative. So, first for this first one, derivative of this would be here the first function, that is 6 into 5, that is 30 times z to the power 4 upon this function is as such. Then this function is as such, that is 6 z to the power 5 is as such, and derivative of 1 upon 2 z square minus 5 z plus 2, just the last integral we had calculated this derivative, that is minus 1 upon 2 z square minus 5 z plus 2 whole square into 4 z minus 5. Now, come to the derivative of this function. This function we are having is actually the multiplication of the two functions in the numerator and the one function in the denominator. So, first the numerator one, and denominator we will treat as multiplication 1 upon this one. So, first function, this one is z to the power 6 plus 1, its derivative is 6 z to the power 5, and all other functions are as such. Then we will go for the derivative of the second function and all other functions as such. The derivative of the second function is 4. So, we would get 4 times z to the power 6 plus 1 upon 2 z square minus 5 z plus 2 whole square. Now, we will come to the derivative of 1 upon 2 z square minus 5 z plus 2 whole square. This we will treat as 1 upon. So, its derivative has to be minus 2 upon this whole function cube and the derivative of this one, and all the functions remain as such. So, we would get is minus and minus will get plus, and 2 upon 2 z square minus 5 z plus 2 whole cube, and the derivative of this inner one is 4 z minus 5, that we have to multiply to the numerator, z to the power 6 plus 1 into 4 z minus 5 multiplied with, that is a square. Now, what we have to actually evaluate? We have to evaluate the second derivative at z is equal to 0 multiplied with half. Second derivative we had calculated. Now, we have to evaluate it at z is equal to 0. If I have to evaluate it z is equal to 0, you see that is as such we have got very lengthy expression, but with z is equal to 0 the first expression is 0, with z is equal to 0 the second expression is 0, as well as the third expression is also 0. So, the first three expressions would vanish at z is equal to 0. When in the fourth expression we are keeping z is equal to 0, what I would get in the numerator as 4. In the denominator this is 0, this is 0, here is 2, 2 square is 4. So, what we would get minus 4 upon 4, and the last expression, this is 2, here we would get 1, here we would get 5 square. So, 2 into 5 square, and the denominator is your 2 to the power 3. So, 1 2 is getting cancelled out, we are getting as 4, and the numerator is 5 square, that is 25. So, here we have got as minus 4 upon 4, and here we have got is plus 25 upon 4, that is net solution would be actually 21 by 4 multiplied with half. So, we get 21 by 8. So, we have got the residue at z is equal to 0 is 21 by 8, while as the residue at z is equal to half was minus 65 by 24. Now, we had calculated our both the residues. So, now we are ready to answer our question. So, we are having is that the residue at 0 is 21 by 8, residue at half is minus 65 by 24. These are the two isolated singularities inside this unit circle. So, the integral of 0 to 2 pi cos 3 theta upon 5 minus 4 cos theta d theta, which we have changed into the contour integration as I upon 2 integral along the unit circle of z to the power 6 plus 1 upon z cube into 2 z minus 1 into z minus 2 dz. This is by residue theorem has to be I by 2 times 2 pi I residue of f z at z is equal to 0 and of f z at z is equal to half. We had just substitute this 21 by 8 minus 65 by 24. If we make it 1, this would be 63 by 24, that is we are getting is minus 2 by 24. This I and I would give minus 1, 2 is getting cancelled out. So, I am getting is minus pi outside. Here I am getting is minus 2 upon 24, that is it is pi by 12. So, finally, we have got the answer that integral of 0 to 2 pi cos 3 theta upon 5 minus 4 cos theta d theta is pi by 12. Now, let us see one more formula Let us see one more example. Evaluate the integral minus pi to plus pi d theta upon 1 plus sin square theta. Now, you see in this integral our interval of integration is from minus pi to plus pi. Integrand is also having a square of sine function. So, first we would make it into the form of either cosine theta sin theta form of or cosine a theta and sin a theta form, only then we would apply our results. So, first take this function, the denominator 1 plus sin square theta. This we do know, we could write sin square theta as 1 minus cos 2 theta upon 2. So, 1 plus 1 upon 2 cos 1 minus cos 2 theta, this says is it is 3 minus cos 2 theta upon 2. So, what we have got now, our integral minus pi to plus pi d theta upon 1 plus sin square theta, we could write this as integral from minus pi to plus pi 2 upon 3 minus cos 2 theta d theta. Now, this has come to the form of f cos a theta sin b theta. So, we could use our transformation, or we could, but here the integration interval of integration is actually from minus pi to plus pi. In our integrals we have taken the integration from 0 to 2 pi. Now, let us see is that is what this minus pi to plus pi is. I can rewrite this integral as the sum of two integrals. For the first integral it should be minus pi to 0 of the function, and in the second one this integral should be from 0 to pi. Now, if I rather than having it as from 0 to 2 pi, if I am breaking it into two parts, one is from 0 to pi, another is minus pi to 0. So, if I apply z is equal to I theta, my theta would range say in the second interval as 0 to pi only, that says we would have only half of the unit circle. What would be the range minus pi to 0? Let us see it here. So, first we are going to make the same our substitution, that z as e to the power I theta. So, my d theta would be dz upon I z, and cos 2 theta from here would be 1 upon 2 z square plus 1 upon z square. Now, we see this limits which we are having minus pi to plus pi. This I am breaking as minus pi to 0 and 0 to pi. So, let us first see this 0 to pi, 0 to pi. So, now this we are saying is that we are talking about this say polar coordinates. So, I would have r is 1 and my theta is ranging from 0 to pi. That means, on this unit circle we are going with this counterclockwise. On the first integral actually we are ranging from minus pi to 0. So, if we see in the polar coordinates this theta, if we are measuring, this way of the measurement is called the positive and this way of the measurement is called negative. So, minus pi would be actually we are starting from 0 and running over here. So, this point would be minus pi. So, when we are saying is minus pi to 0, it says is we have to move in the circle unit circle from minus pi to this one. That says is this integral 0 to pi we have covered this half circle, upper half circle, and from minus pi to 0 we are covering lower half circle. What is the direction? 0 to pi, the direction is counterclockwise, minus pi to 0 again the direction is counterclockwise. That says is actually this integral, if I join it minus pi to plus pi, we are actually moving from here to here, that is the full circle. That says is it is same thing as having, we can again change it to the unit circle. So, let us see. We do have integral minus pi to plus pi 2 d theta 3 minus cos 2 theta changed as the integral, contour integral on the unit circle. Here we are substituting this d theta as dz upon Iz. So, that Iz have written in the numerator 2 upon Iz, and 3 minus cos 2 theta is 1 by 2 z square minus plus 1 upon z square. Simplify it, this would be z to the power 4 plus 1, and here we would get 3z square, and 2 is also so 6z square, and this 2 we would get upside, that is it would be 4, then z square would also go z square will also go up. So, this we would get only z, because z square upon z is z. So, what we are getting in the numerator 4z, in the denominator I is coming in the denominator, 6z square minus z to the power 4 minus 1. Again 1 upon I would write as minus I, and that minus sign I would change here, that is z to the power 4 minus 6z square plus 1. So, we do write that our integral changes to I times the contour integration on the unit circle of the function 4z upon z to the power 4 minus 6z square plus 1. Again my function is coming as a rational function, that is which is the ratio of two functions pz and qz. So, pz is 4z, qz wherever this would have zeros at those points, this function would have singularities. We will find out that is what kind of those singularities are, and we have to find out the integral, and of course, it is looking that this would have zeros are always isolated zeros. So, the singularities will also be always are isolated singularities. Let us see z to the power 4 minus 6 z square plus 1. We would write it as z to the power 4 minus 2 z square plus 1 minus 4 z square. So, the z to the power 4 minus 2 z square plus 1 would be z square minus 1 whole square minus 4 z square, that is minus 2 z whole square. We would use x square minus a square as x minus a into x plus a. So, we would get z square minus 2 z minus 1 into z square plus 2 z minus 1. Now, let us see one by one this z square minus 2 z minus 1. So, if I take it here plus 1, I would get minus 2, z square minus 2 z plus 1, that is z minus 1 whole square minus square root 2 of whole square. Again we would do the same inequality. So, first one I would get z minus 1 minus root 2, z minus 1 plus root 2. Similarly, here we would get z plus 1 minus root 2 and z plus 1 plus root 2. So, I am getting the all the factors as z minus root 2 minus 1 into z plus root 2 minus 1, here z minus root 2 plus 1, z plus root 2 plus 1. So, what we have got this denominator is having zeros at 1 plus root 2, at 1 minus root 2, here again 1 minus minus of 1 plus root 2 and minus of minus 1 minus root 2. That is, we are having that fz has simple poles and all the zeros are of are simple zeros. So, we would have the simple poles at plus minus 1 minus root 2 and plus minus 1 plus root 2. So, my function is having 4 isolated singularities at plus minus 1 minus root 2 and plus minus 1 plus root 2. Our contour is unit circle. So, certainly plus minus 1 plus root 2, 1 plus root 2 plus side would be outside this one, minus would be outside this one. So, this these two isolated singularities would be outside our pole, our region of this from the region from the interior of the contour. We would have only two singularities which are inside the interior. One is your 1 minus root 2 and another is minus of 1 minus root 2, that is root 2 minus 1. So, we are having now we have to evaluate a contour integral of a function which is analytic on inside to the interior unit circle except at 2 points, 2 isolated singularities. So, I can use the residue theorem and find out the integral using the residues at both the isolated singularities. Let us see, using the residue theorem I would get this integral I times contour integral of 4z upon z to the power 4 minus 6z square plus 1 dz as I into 2 pi I times this integral is 2 pi I times residue at z to the at z is equal to minus 1 plus root 2 and residue at z is equal to 1 minus root 2 of the function f z, where f z is this function. So, now first we will calculate our residues. My function is 4 z upon z to the power 4 minus 6 z square plus 1. This is of the form p z upon q z. We would use, and our isolated singularities both are simple poles. That says is we would use the formula for p z naught upon q dash z naught. So, let us find out. So, we will use this formula, residue at z is equal to z naught of f z is p z naught upon q dash z naught, when z naught is a simple pole. Q dash z would be 4 z cube minus 12 z. We could rewrite it as 4 z times z square minus 3. So, what will be p z naught upon q dash z naught? This would be p z is 4 z. So, 4 z naught upon 4 z naught into z naught minus 3, z naught square minus 3, sorry, this should be z naught square minus 3. So, what we would be getting 1 upon z naught square minus 3, this is what is p z naught upon q dash z naught. So, the residue at z is equal to z naught would be actually 1 upon z naught square minus 3. Now, use this simple formula for calculation of residue at both the points, that is minus 1 plus root 2, it would be 1 upon minus 1 plus root 2 whole square. What we would get? 1 plus 2 minus 2 root 2. 1 plus 2 is 3, 3 minus 3 is cancelled out, I would get 2 root 2 with the minus sign. So, we would be getting minus 1 upon 2 root 2. Similarly, the residue at z is equal to 1 minus root 2. Square of 1 minus root 2, again 1 plus 2 minus 2 root 2, 1 plus 2 and 3 will cancel it out, we would again get minus 1 upon 2 root 2. So, now we are getting, so you use this residue theorem, the integration would be I times 2 pi I residue at minus 1 plus root 2 plus residue at 1 minus root 2, which is I into I, that is minus 1, 2 pi. Here what we are getting is minus 1 upon 2 root 2, again minus 1 upon 2 root 2, we would be getting it as minus 1 upon root 2, minus 1 is already outside, I would get 2 pi upon root 2, that is square root 2 pi. So, we have got one more formula, that integral of minus pi to plus pi 1 upon 1 plus sine square theta is square root 2 pi. This you do remember that you have used it as a formula, and proof of this was tedious. Of course, here also it is not very simple, but the methodology is much simpler. So, we had seen today that the residue theorem or residue integration method is not helpful only in evaluation of complex integrals, rather we can use it in evaluation of real integrals as well. Today we had seen the evaluation of definite integrals, and those definite integrals we had seen which are involving the sine and cosine function. Now, from here you could see we could actually solve a lot kind of real integrals, where the function or that the variable, real variable, we are changing it to into sin theta and cosine theta, and we are getting the integral of the form 0 to 2 pi and function of sin theta cosine theta, whether it is simply sin theta cosine theta or in the power of sin square and cosine square, or we are changing them into the sin m theta cosine m theta. All those integrals we could solve it using this residue integration method, and it gives a simple way of solving, or you could say is one more way of solving the real integrals. We would learn some more applications of residue integration method and residue theorem in coming lectures. Today we have learned only for the definite integrals. So, that is all for today's lecture. Thank you.